This section is on properties of radicals. So we're going to take a look and understand how we can divide and subtract, divide and multiply radicals and see what we get as a result. Here's what I want you to remember. When you work with radicals, think about just as if they were just variables. Okay? Keep that in the back of your mind. Think about a radical statement as a variable. So for example, if I had 2a plus 3a, it's
5a.
5a plus. Okay? 2a plus 3a is 5a. So in this problem in a moment, we're going to see where we're going to be adding, subtracting, multiplying, dividing different things. Keep that in mind. Think about those rules. Okay? Same thing goes when you're dividing. If you were dividing two numbers like 18 divided by 6, everybody knows the answer is 3. But it's because you can break up the 18, right? You can break up the 18 into 6 and 3. The 6 is canceled, leaving behind the 3. Keep that in mind with this as well. Okay? All right. So our first two rules are just going to be our rules of multiplication. If you're multiplying radicals, if you're multiplying two things on the inside of the radical, they can be multiplied together. So for example, if you had like radical 3 times radical 4, it's radical 12. Or radical 12 is really radical 4 times radical 3. You follow what I'm saying? It's a biconditional. It goes in both directions. So the square root of 12 can be broken into root 4 times root 3.
Oh, yeah.
Or root 4 times root 3 can be written as root 12. Keep that in both directions for this, because it might help you to multiply, get a big number, and then break that big number down to smaller numbers, and you'll see what I mean. Same thing with division. Okay, when you're dividing two things under radicals, you can separate the radicals. And we saw this the other day. Remember yesterday we did the radical 9 over 25. We made it root 9 over root 25 and reduced that to 3/5. Same rule applies, but we're going to take a look more in depth. So how about part A? If I wanted to simplify part A, what could I break part A into? What factors that are able to then simplify even further, Hannah?
25.
Why did you pick 25?
Because it's I forget what it's called.
It's a perfect square. Okay? So what are you doing? You're looking for perfect roots. Don't say squares always now. Say roots, because look at choice C. At problem, or not choice, at exercise C here, we're going to look for not perfect squares, but perfect cubes. So for part A, we break it into 25 and 3. And you know what I always do? I put the perfect part in the beginning. Why do I do that? Anybody know?
Because when you
Simplify?
simplify it, it's going to come out to like 5 and then root 30.
Very good. Because we write it with the actual integer in the front, right? The simplification goes in front. What is the 5 really, in essence? The 5 is like a what? Coefficient. Remember what I said? Think of radicals as variables. So if you think of root 3 as x, it's like 5x, right? So 5 is like a coefficient now. Keep that in the back of your mind. Write a little note, please. The 5 is like a coefficient in the answer I'm talking about right here. And you'll see why you're going to write this down. Okay, when we add and subtract, which we probably won't do until tomorrow. Okay, but when we do that, we're going to have to remember to think of that number in the front as a coefficient. It'll make life so much easier on you. How about part B? How about part B? What do you want to start with? Go ahead.
Multiply them together.
Yeah, because root 8, you can break that into 4 and 2, but then you can break 6 down. Let's multiply them together first, or we can break them down first. Either way, I'll multiply them together. So 8 times 6, you get? Brain fart. So negative root 48. Dave, what do you want to break this into now? Okay, but 24 is not a perfect square. I agree with you. I want to say 24 and 2. Go through perfect squares.
16 and 3.
There it is, 16 and 3. So here's what you're doing in your brain right now. Here's what's going on. You see the number 48. You say, does 1 go into it? Sure, it does. But that doesn't do anything for me, right? That's a perfect square. Does 4 go into 48? It does. But it leaves behind a 12, right? 4 times 12. And then 12 could be broken down further. That means you haven't reached the biggest perfect square yet. Again, you want to find the biggest perfect square that can go into 48. Sure, 4 does. But when you break it down, it would be 4 and 12, and then 12 gets broken down to 4 and 3. So if you can break things down twice, it means you're not at the biggest one yet. And since we got 4, and then 12 breaks into 4 and 3, you get 4, 4, 3, which is where the 16 times 3 comes from. 4 times 4 times 3 is really 16 times 3. So keep going to bigger perfect squares. After 4, you try 9. Does 9 go into 48? No, it does not. 16 does. It goes in 3 times. And then the other number left, that 3, cannot be broken down to anything else that can be a perfect square, so you're done. Okay, so here's your process. Give me a second, okay? You can start it several ways. You could start by saying, well, it's 4 times 12, really. But then 12 breaks into 4 and 3, right? So that's what would happen here. You would get 4 times 4 times 3 underneath the square root. But this 4 times 4 is really 16, isn't it? So you end up having the perfect square of 16 because of these two 4s. So this is what I'm saying. When this 12 can be broken down further, you're not there yet. So keep trying to find a bigger perfect square. Arthur.
So it'll always be able to, like, break down into...
No, not always. And then you can't simplify. You would say there's no simplified form or nothing further. The problems I give you that say simplify are probably going to be able to be broken down. Okay?
So your answer is 4 radical 3.
So the answer is 4. Good. 4 radical 3.
Negative 4, right?
Yeah, thank you. Carry down the negative. Thank you. Who was that? Worth. Don't forget that negative. Yes.
Why wouldn't you break down 4 into like 2?
What's 2 times 2? If you break these both out as 2s, don't they become back to a 4?
Oh.
You could do that, Ida. That's fine. So Ida said, hey, there's a 4 and a 4 here. Bring them both outside as 2s, but then 2 times 2 outside ends up giving you the 4 anyway. So my thought is always to go right from here, okay, to here. I don't use these steps. I was showing that if you had used them, you would get the same answer. All right? How about the next one? How about the next one? This is tough. This is tough. It's not easy. What do you want to start with?
Well, I was probably two together, so I did keep that.
Mm-hmm.
250, yeah.
Definitely to start with, because you can't break down 25 into a perfect cube. What are your perfect cubes? Should we list the perfect cubes so we know? On the right side, let's list them. Who wants to run through them? What are the perfect cubes? Give me some of them at least. Go ahead.
8.
Let's start with 1, and then 8. Yep, good.
8.
3 cubed.
Oh, 3, sorry.
Call it out. Call it out. 27.
I don't know.
4 cubed.
64.
5 cubed.
125.
6 cubed.
216. She's looking it up.
7 cubed.
7 cubed. 343.
Yep.
8. I don't know what 8 cubed is. I only know the 7.
I don't remember 8 cubed either.
Well,
It's 5 and change. 524 or something, or I don't know. Something 5 something.
Yeah.
Oh, it's got to be 5. Let's see.
I know it's
64.
64. Something 32. 5. Something 2.
I know
Okay.
what 10 cubed is.
Now let's stop here.
I see what you're
It's not funny.
Let's stop here to remember that, like, at this point, it doesn't make sense, right? We would actually just evaluate the number with a decimal. So the one you should know up to, you should really know these first 5 here. Okay?
How good I know that?
You should know those first 5. Hannah.
You can do 125 times 2.
Yeah, and that's what we're going to break this into. So everybody see the 250 on the side over here? 250 breaks into 125, which is a perfect cube, times 2. And we're looking for perfect cubes. So we write this as the cube root of 125 times the cube root of 2. Again, cube root of 125 times 2, that's 250. But then the cube root of 125 is 5. So 5 cube root of 2. You need to be very careful. Those of you know who they are, I'm not going to call you out, that have terrible handwriting. Need to work on it a little bit. Not like, doesn't have to be perfect, but your indices need to be very clear. These little 3s I've seen last year, it was scary when I was grading. I couldn't tell if the 3 was in front as a coefficient or if it was an index. So please emphasize it. Put the little 3 in between the little v in the radical symbol. Okay? See this little v here? Put the number in between it. If it helps you remember that. Fit it in there.
Well, like, on the first one, wouldn't you just get the same answer if you divided by 2, and then you get the same answer for the second one if you divided by 5?
Where are you looking?
Like,
Sorry.
if you just divided, like, b, both of them by 2, you would get 4.
Are we on part A, B, or C?
Part b.
Okay.
Yeah.
Divide them both by 2.
It would be 4 and 3.
But I thought we were on part
And
2.
then, we are.
I didn't know you were going back to part B. Sorry.
Yeah, no, and then part c, you divide it by 5. Both of them by 5, you get 5 and 2.
And you get 5 and 5. Yeah, you can do that also. You can break. So Arthur makes a good point. Break this into 5 times 5. Break this into 5 times 2. It's 5, 5, 5, 5, 5, 2. The 5, 5, 5 is really here, bringing it down. Yep. Same thing here. 4, 2, 3, 2. Right? The 4 comes out as a 2. The 2 2's come out as a 2, leaving behind the 3. You could always break them down like that, yeah. So what Arthur's saying is this. Can we break everything down to its prime factors? So he's using the prime factorization. That works. It might be a longer way to do it sometimes, but that does work, for sure. That's good. How about part D? How about part D? There's an easy way and there's a difficult way for part D. There's an easy way and a difficult way. Give me the easy way. What do you think for part D? Worth?
If you remember from the previous slide, you're going to change that to radical 120 over 10.
Yeah. So put all under the radical. And then just divide those numbers. What do you get, Worth?
You get 12.
What do you break it down to, sir?
Simplifies to radical.
2 radical 3. So we break the 12 down. So root 120 over 10 gives us root 12. Break the 12 down into 4 and 3, making this radical 4 times radical 3, which becomes 2 radical 3. Okay? Good. If you tried to do it the other way, you'd break down the 120. You'd have to try and find something that goes into 120 as a perfect square, but then in the end, you'd have to still reduce it. You'd be doing so much more work. So use the rule from the last slide, okay? That's one of those examples where you might as well divide because they are both divisible by 10. Any questions on this? Does it make sense, the idea? Who can recall or restate what we did? Give me a statement, because the next part's going to get tougher, so you have to make sure you really do get this. What did we do? What are we looking for? How do we do this? What are you thinking when you're doing these problems? What are you thinking when you're doing these problems? Come on, somebody. I'm seeing hands. Thank you, guys. I answered a few questions already. What are we doing? We have to stop then and go back if we're not clear, because I should see a few hands up. If I only see 3 hands up, it means that I'm not doing a good job. So let's go back. Let's go back to part A and start over. So for part A, how do I break down 75?
25 and 30.
25 and 3. And then what do I do with the 25?
And then you take the GCF, or not the GCF, the square root, sorry.
Good.
5.
Good. Becoming 5.
Make it a coefficient.
Yeah. Okay? So if you just explain that, how come we can't explain what we're doing? Can somebody explain now? Liam, go ahead.
We're like simplifying it to the most simple.
Okay, but by what means? What are we looking for? What is going through your mind? I'm asking you to go through your thought process. Chris?
Take the greatest perfect root
Take the greatest perfect root, good, and then?
and break it down.
Yeah, break it down as much as you can. And then once you get to that broken down stage, Chris, then you do? Yeah, just simplify. Okay? So you need to be able to explain what you're thinking. And by doing that, it helps you know what you're doing. A lot of you guys just nod your head in here and then go home, and it seems like, sometimes in the homework, you get stuck because the thought process isn't there. So be able to answer that kind of a question, all right? Go on. Let's take a look at a few that are a little more complicated. Okay, and you can see right away why I was saying that. These get more complicated as we go through them. How about part A here? How about part A? What would I do in part A? Sorry.
You can separate 3 and A from together and then have B squared.
Why?
Because they're all being multiplied by each other.
Yeah, and which one is a perfect root in this sense?
B.
Yeah, the b squared is perfect, right? Just like it was like, imagine if this 3 was a 9. You could bring the 9 out, right? And make it a 3 and square root it. The b squared is a perfect squared. So break this into radical b squared times radical 3a. Separate it. Put all your perfect squares in one of the radicals. Put all your non-perfect squares in the other radical. And then simplify the one that you bring out on the left. What's the square root of b squared? Yeah, now this is a little tricky. It's actually absolute value of b.
I saw that.
Okay, because really think about it. What numbers can b take on? B could be -3, and when you square it, it becomes 9. And then you get back to the square root, it still works. So whenever you do this, it's a kind of a rule to remember, put absolute value around that. Try any number for b. Okay, if you think about what b is, if you try 3, well then -3 works also. If you try 4, then -4 works also, because you're squaring it and then you're re-square rooting it, in essence, okay? You're squaring the number, and then you're taking the square root. So a negative or positive works, so we just put absolute value there to represent that, okay? How about part B? How about part B? Go ahead, Arthur.
Well, you could separate 49 and y to the 5th.
Okay, so 49 is definitely a perfect square, right?
And then,
Now, I could keep going, though. What could I take out of the y to the 5th?
2, or, yeah, you can take out 2 because then it'd be 5 over 2. And then,
Kind of, but I want to know what perfect squares can I take out of there? y to the fifth is really this. Let's take a look. Look up at the board up here. Okay? See the 5 y's there? If I group them, isn't this a perfect square? Isn't this a perfect square if I put them together? So technically I could do this. And you're not going to write it out like this. It's easier to do. And then you'll put the y over here. Take a look. Remember your exponent rules? Y squared times y is really what? Y to the fifth. So I have not changed the value at all, but I'm taking out these two perfect squares here. What do they become when I take the square roots?
It would be y squared.
Well, 49, yeah. Absolute value y times radical y, which is in essence y squared. And we don't need the absolute value there anymore, because you're squaring it anyway.
7.
7, thank you. Thank you.
Gotcha.
Brain fart. Okay? But the idea is that you're taking out two sets of y squareds. Now, would you really do that? What would you take out instead of taking out y squared like 2 times or 3 times or 4 times? Yeah, you take out y to any even exponent. Reaction there, wow. Take out y to the 4th instead. And then you think about your exponent rules with the radicals. What's the index that's up here really?
2.
There's really a 2 here. 4, right? This 4 right here divided by this 2 that's really here is 2. Okay, that's that rule from yesterday that we went over. So this is your final answer at the bottom here. 7y squared times the square root of y. So the 7y squared is now thought of as like a coefficient, which is weird. Now we have variables in our coefficient. Okay, but just think of it, okay? Keep it in the back of your mind. How about part C? We no longer have a square root, but a cube root. Part C, David.
The cube root cancels out with y, the absolute value of the bottom.
Okay.
And then for the top, you can break it down to w to the third w. And then that also cancels out, and you get the absolute value of w and w to the third over y.
I forget, I'm trying to think. Does absolute value go through for the odd?
Oh wait, it actually doesn't.
I don't think it does, because I'm trying to think about my numbers for a
Because
second.
it's either positive or negative.
Yeah, it has to do with the fact that you can have negatives under there, so it doesn't matter for that one, okay? So we end up getting the W here, the W out in front, all over the Y. Sorry, I wanted to just think about that. I was wondering why you were saying absolute value, but it doesn't for odd. For evens it does. Okay? Yeah.
Can you just explain that again?
Sure. Absolutely. So we start up here, right? We start by breaking this down into the third root of w to the 4th over the third root of y to the 3rd. But what happens here, Ida, with this? What's the cube root of a cube? Yeah, the number itself. So this just becomes y. Is that cool?
Yeah.
Then we take this one here and we say we need a perfect cube. So break w to the 4th into w to the 3rd times w, because this is w to the 4th. W to the 3rd times w is w to the 4th. The cube root of w to the 3rd is w, and then this cube root of w gets carried down. I know, a lot's going on. Just follow the logical steps. Look at the placeholders. This cancels, giving you the w. This cube root of w is still here. This cube root of y cubed comes at y, and that carries down on the bottom there. Go from line to line and look at what replaces each location. Okay, so this is why I asked you to make that statement that Chris made. He said we're looking for the perfect root, whatever it is. In the last example, we looked for the perfect square in part B. In part C, we looked for the perfect cube. How about part D? How about part D? And this is a bit of a trickier one. Square root of 9w squared plus 9u squared. What can you do here? And remember, the goal is to factor this so that you have a perfect square. You're always trying to factor what's inside. We've been factoring the whole time, whether you realize it or not. Right? 75, we broke into 25 and 3. Isn't that factoring? Factoring isn't just variable. So now factor, giving me a perfect square. What can you take out? Every hand should be up right now. Come on, people. What can you take out? Boston.
Pretty much the whole thing.
So tell me, what number can you take out? What number is in both? 9. So take out a 9 right away. Okay, all I said was factor, so right away look for your factors. Okay, so we start with that. Isn't 9 a perfect square? It absolutely is. This is a little bit tricky though. This is not a perfect square. It wants to seem like it is, but it's not. And let's explain why. Okay, let's break it down a little further. We'll write this way. Okay, your old knowledge needs to come in. So when I say, what do you take out? What do you factor? There's your GCF 9. Well, radical 9 is just 3. That's easy. Now here, it seems like you might want to say, oh, that's W plus U. But are these factors? What are they? That's the word I used a few weeks back. When you were factoring, and you couldn't factor something that didn't work, we called them, if they're not factors, they were, what was it? Add-ins. Yeah, two things that add together. So these two things are added together. They're not multiplied. So you cannot just reduce them. Okay, and try it with numbers. Pick numbers and try and work it and see if it works out. It won't work out the same way. So you leave that. It's not reducible. Okay, you're done with this problem. 3 times the quantity square root of W squared plus U squared. Okay, 3 is our coefficient here. And think about it this way. The only way this would have worked is if you could have gotten something like W plus U times W plus U. Right? But you cannot factor this. There's nothing to factor that into. How about the last one? How about the last one? You can most definitely do this one. Hannah.
Well, you would factor, for like terms or whatever, and so you got under the big square root sign x plus 6, x plus 6.
Yeah. And that's the key here. The factors are the same. So Hannah, how would I write this?
Oh, you can take one.
How would I write it though? X plus 6.
X plus 6 squared.
Yeah, and then the square and the square root cancel. Okay? Leaving behind. And we should put absolute value in here, sorry, because we want this to be a real answer. Okay, again, do you see why we're taking the absolute value here? Because no matter what, for this problem, we want this to be a real number under here. Does that make sense, that last one? Yeah? No, maybe? Okay. Go ahead. It's the same process, just looks different. Why is there what?
Why is there no radical?
Well, the goal of this is to reduce it, right? To get rid of the radical. So when you get a square, the radical and square like cancel each other out in a sense, right? If you had 3 squared under a radical, well, what's 3 squared? It's 9. And then square root of 9 is 3. So 3 squared, those just cancel each other out. You get the 3. Okay? Just like Ida, go back up here. Go back up to this one, right? When we took the square root of b squared, we got rid of the radical. We just left with the absolute value of b. Just showing that it's whatever b is but the positive value. Okay? All right. The last thing I want to talk about is just rationalization. Has anybody seen this when you rationalize the denominator? Let me go over something first. Well, we're going to talk about what it is. It was really useful when there was no calculators around. Nowadays it's not as useful unless you go into simplifying things with a lot of variables in calculus. The radical is really important to know how to work with in calculus. There's a lot of square root functions, so you're going to see a lot of them. But the process itself is a little bit outdated simply because of the fact that we have calculators now. A long time ago, when there were no calculators, how did people take square roots? Like, what's the square root of 5? What is it? Anybody know? No, you would type it in, you would figure it out. But it's between what? Yeah, it's between 2 and 3. The square root of 4 is 2. The square root of 9 is 3. So the square root of 5 is somewhere between 2 and 3. But we don't exactly know where just by looking. There are calculus techniques that you can actually find the exact decimal value without using a calculator. How cool is that? You can get like as many decimals as you want without ever using a calculator. Now, to do that though, you need to be able to do what's called rationalization of the denominator. We had tables a long time ago that listed all the radicals. So if you had something like this, if you had something like radical 3 over radical 5, you wouldn't want to do this because this is a decimal, you have to find it in the table. You'd find this as a decimal in the table, and then dividing decimals without a calculator is a really messy job when those decimals go on for a while, right? Think about that for a little. That's really annoying. So you wouldn't want to do that. You'd really want to just have one radical in this problem, make it easier. So rationalization, what we're going to do, is getting rid of the radical in the bottom and only having a radical up top. What could I multiply the top and bottom by that would make the bottom now a perfect square? Hannah. Not 5. Close. You're missing something. Nope, you're saying it the wrong way.
1/5 or 1/5,
Square root of 5.
Square root of 5. You said 5, then you said 5 squared. Square root of 5. Because if I multiply by square root of 5, what does the bottom become now? What's the bottom, everybody? What's root 5 times root 5? It's just 5. Because this is really radical 25. Agreed? Isn't this really radical 25? We've made a perfect square. We look for radical 25. We've made a perfect square here. What does the top become? Radical? Yeah, radical 15. All over 5. Well, now, this was years ago. Now it doesn't matter really because the calculator, but this is the reason. You could look up what radical 15 is and then just divide it by 5. That's so much easier to divide by an integer. You don't want to divide two decimals by each other. So now you look up what radical 15 is in your table and then you just divide that answer by 5. Okay? It's a lot simpler to do that. Or multiply by 0.2. Right? Multiplying by 0.2 is really 1/5. So instead of dividing by 5, I can take whatever this decimal is and multiply it by 0.2. It's really easy to do long multiplication. It's much more difficult to do long division with two decimals. So that's the reason. Does everybody understand? Okay, it doesn't really matter as much nowadays, but you're going to learn the technique and you're going to need to know how to do it because you guys are on pace to go on to AP Calc. That's the goal. And when you get to 12th grade, you actually study some real applicable math. That's where you start learning a lot about those. Remember those like oil leaking problems and stuff? And those height problems? That's a lot of calculus. You'll see that there. Okay, so let's go through a few examples. Now, the first one is pretty simple, and then after that they get a little more difficult. What would I multiply the first one by? Both top and bottom. Yeah. So I'm going to start by rewriting it like this, right? And then I'll multiply by root 3 over root 3. Why can I multiply by root 3 over root 3? What is that really? 1. Isn't radical 3 over radical 3 1? I'm not changing the value. Thus my answer is root 21 over 3. It's really root 21 over root 9, but root 9 is just 3. Are we clear on part A? Now we have to extend that to part B. Part B says root 3 over A, so I start by rewriting it like this. What do I multiply by? Use part A as an analogy or as a guide for this. Austin?
Root A.
Yeah, very good. Over root A, please say, right? So root A over root A. That gives me in the numerator root 3A, and in the denominator? Let's put our absolute value of A here. Okay, so again, the goal is to get C to the 5th here. So if I have C to the 2nd already, how many more do I need?
C to the 3rd.
Yeah, so I multiply by the 5th root of C to the 3rd on the top and bottom. So this was the starting point. I'm going to multiply by the 5th root of C to the 3rd on the bottom so that I get C to the 5th now. But if I do it on the bottom, I have to also multiply on the top. So on the bottom now, what do you get? What do you get? The 5th root of. You get rid of it if you get rid of the 5. You have to do the both there, Ida. So either it's C or it's the 5th root of C to the 5th, which in essence becomes C. Okay? So I'll give the intermediate step because people were getting confused the other day. So this becomes the 5th root of C to the 5th, which is just C. Okay, that is just C on the bottom there. And I'm going to move over further and make this look a little bit better. Okay, the 5th root of C to the 5th is just C. So you've rationalized the denominator. What about the numerator? I'm multiplying two things that are 5th roots. What do I just do?
You just add the power.
Yeah, add the exponent. So it's still the 5th root of C to the 4th though, and I can't go any further with that. Alright, so this is your final answer on the far right. The 5th root of C to the 4th all over C. Really weird, I know. And would you ever really do this nowadays? Probably not. But when it comes to solving things algebraically, especially when you get to harder math, you're going to start doing this. So I'm trying to give you that skill right now. Okay, so you see that. The important ones are the ones with numbers for sure. So something over radical 3, being able to multiply by root 3 over root 3. Okay? Or reducing it and then multiplying by whatever it is. I'm gonna leave part D out for now.